So Andy, I'm turning it over to you.
Excellent. Thanks, Jean. And thanks, Doug. That was a fantastic presentation and really good overview of wetland types, and it ties really nicely into what I'm going to talk about now. And what I'm going to talk about is the application of the wetland understanding that Doug has just described in terms of wetland types, and also the classification systems that he rounded out with, to real-world resource management issues, and how we take those concepts and take the classifications and apply them to problem solving on the landscape. So I'm going to look at three different examples in order to illustrate that. We've been doing work with these classification systems and with wetland science across the country, and there's some really good examples of how to apply, in particular, the landscape level inventory techniques, so the things like the National Wetlands Inventory and the coordinate classification, as well as Doug described it, HGM and LLWW, hydrogeomorphic attributes, to both inventory and then provide guidance for how we might begin to manage some of these resources. So I'm going to look at a climate warming example from Alaska, and then I'm going to talk about a project in New Mexico where the objective was to manage some of the impacts of grazing on high elevation wetlands. And then we're going to look at a flood attenuation example from Wisconsin. All of them tie to the functions and benefits that Doug so accurately described. So I'll try and sprinkle some of that into it. Starting with Alaska. One of the biggest challenges in Alaska, of course, is the size of that state. I always like to show this graphic of Alaska superimposed on the lower 48 just to give folks a perspective of the land area that we're dealing with in that state in order to try and address wetlands and wetland issues. And it's not just, of course, the size of the state, but it's also the diversity of the state, where we have, high Arctic permafrost conditions in the north, down through boreal forest types in the central region and the south central region, right down to the lower southeast, where we have rainforest conditions along the Pacific coast. So there's several challenges in Alaska, and also the amount of money available to address both wetland inventory and then wetland management is not sufficient for a state of that size. So several challenges that lead to a very, very interesting landscape. One of the other things is that Alaska is also the front line of climate change, climate warming in this country, where we deal with northern landscapes that have extreme susceptibility to climate fluctuation. Any subtle change in climate can cause a big impact on the ecology of the state and the various conditions of different land cover and habitat types. And some of the issues that are on the front burner for addressing with an updated wetland mapping or wetland inventory process include habitat inventory, particularly, and one good example is migratory birds, where birds are being impacted, habitat is being impacted directly by things like coastal storm surge and sea level rise and warming temperatures. Erosion, flooding, and storm intensification are huge issues in Alaska. The frequency and intensity of Pacific storms has grown tenfold over the last 20 years, and it's causing some huge issues from a wetland management and habitat management standpoint. And I'll show a couple of examples of that. One of the big results of that is shallow lake drying and draining, and we've seen some significant issues with that in wetland temporal studies, change over time studies that are showing dramatic change in very relatively short periods of time. Permafrost degradation and thermokarst feature development is also a big issue in Arctic Alaska, where the modifications, the warming of climate is causing changes in melting of the permafrost landscape, which is creating huge releases of greenhouse gases into the atmosphere as a result of all of the stored carbon that's within those landscapes suddenly being released through the melting and drying and evapotranspiration of carbon. And then vegetation encroachment and rapid succession of vegetation in areas where vegetation, particularly tree vegetation, previously did not exist. Again, that's a function of temperature, but also of drying. And I'll show just a quick example of that. So the coastal erosion inundation issue is dramatic. There's a huge impact on coastal settlements, particularly native settlements in Alaska. You can see by these before and after pictures, the before picture in the upper corner and the after picture of the same community in the lower picture. The effect is significant, and there's huge issues around relocation of these settlements and management of the coastal wetland community in order to mitigate some of these inundation and storm surge issues. There's not a lot you can do in a situation as serious as the one in the lower picture, where the entire landscape has been flooded by storm surge, but limiting development along these coastlines and using natural barriers such as wetlands to control and mitigate the coastal storm surge is a huge opportunity, and we can't achieve that without a good inventory of wetland features to support it. I had mentioned earlier shallow lake drying and draining happening over relatively quick periods of time. These are two aerial images of the same location on the Yukon-Kuskokwim Delta in central western Alaska. The image on the left-hand side was taken in 1984, and you can see if you look at the center of the photograph, this serious chain of lakes running north to south through the image. And then if you look at the image on the right-hand side, which was taken in 2010, you see that several of those lakes have been completely drained out, and a new river has developed through the center of this image. That's totally due to storm surge and influx of marine intrusion into what were freshwater environments, causing the barriers, the permafrost barriers that created these lakes to melt, and having the fresh water that used to inhabit those lakes to drain out and drain into the ocean. These are significant changes in the environment over very short periods of time, 20 to 30 years of climate change, climate warming, storm surge increase, and in a fragile landscape like Arctic Alaska, the impacts are very large. What's also happening in these environments now is that there are wholesale changes of both vegetation and wildlife due to the fact that we've now created an estuarine environment, which is salt-dominated versus a freshwater environment. And again, these types of changes, documented through wetland inventory and monitored over time, are essential for how we manage the landscape. I mentioned permafrost degradation, thermokarst features. This is just a quick example of what some of that looks like in Arctic Alaska. The features are primarily slump features, and they're occurring where underlying ice is melting and causing the overburden, the soil overburden, to collapse inward. You can see some of in a couple of the lower slides, the slide in the lower left and the slide in the lower right, some of the patterned ground that develops as that happens. Again, really important features to understand because of the release of greenhouse gases that occurs when the ice melts and all that organically fixed stored carbon is released to the atmosphere. It's one of the most significant potential releases of greenhouse gas. I say non-related to human activity, but it's really related to human activity because the climate warming is the cause of it. But it's not a human-produced gas. The gas is inherent in the soil, and it's released as it melts. So it's it's a significant issue, and it's happening broad scale across Alaska, and we don't know about it unless we study it, and unless we have the wetland inventory information to monitor it. The last quick one I wanted to show related to Alaska is vegetation encroachment. Again, we've got a before and after picture. Before, in the upper left corner, you can see a wetland in the kind of center left portion of the photograph, and you can see some of the vegetation surrounding it. over on the right-hand side, and then the picture from 20 years later on, you see the same wetland dried out considerably, gone from a standing water deep marsh to a clustered emergent wetland in the second photograph, and you see the amount of vegetation encroachment that's happening around it. There's actual forest cover coming into an area that was typically wetland in the past. You know, is it an issue? It's an issue because of the wholesale change that's going on in terms of different species occupying niches, habitat niches that they did not occupy previously. How do we manage for it? It's very difficult to manage for it on a landscape scale, but site-specifically, there are opportunities for management, and we can't manage it unless we know it, unless we have the wetland inventory information to tell us what's going on. So just a little bit about the wetland inventory techniques that are being applied to address these issues in Alaska. We've talked about the classification systems, but we haven't talked about how those classification systems are applied in the mapping process. I mentioned in the introduction that one of the things that's driving changes in the inventory approaches is technology. And so technology related to both the ways in which we interpret wetlands on the landscape and also the data that's used to support information about how we make those wetland delineations and how we apply attribution to them. So just want to touch briefly on a couple of things. Automated image classification, there's an example of that in the image in the upper left corner. The automated process is utilizing traditional image types like satellite imagery and airborne aerial imagery, and then automated remote sensing techniques to look at those images, assess those images, and delineate wetland boundaries. The reason I mention it is because I talked about previously the size of Alaska and the cost involved in conducting a wetland inventory. Automated techniques are a way of mitigating that cost. If we can develop techniques that accurately both delineate and provide some information about wetland classification, we can undertake these inventories a lot more cost effectively. And some of the new automated techniques that are being developed right now are directly applicable to doing that. Those techniques as well are supported by what we call collateral data or associated affiliated data that also provides information about the presence of wetlands and the type of wetland that might be present. One of the most important of those is the advent of high-resolution elevation information, typically called either LiDAR in the lower 48 or IPSAR in Alaska. And the data sets that are provided from those provide a picture of the bare Earth surface. And as Doug mentioned in his wetland type discussion, a lot of the wetland types are related to either landscape position or landform type. And basin wetlands, of course, are the classic example of ones that exhibit very distinct topographic signatures. And LiDAR or IPSAR information can be utilized to much more easily and accurately define the boundaries of those wetland types. We also apply several other data types to the wetland decision-making process, including things like local vegetation surveys, the two local soil and statewide soil and information databases, SURGO and StatsGo, which the NRCS folks will be intimately familiar with. And then we're also using different modeling tools. In this case, I'm pulling out CART tools, which are regression tools to analyze and sift through all this data and help us with decision making around how to map them. And of course, there's no substitute for getting out in the field and identifying wetland types before mapping and also verifying wetland types after mapping. This is just a really quick example of LiDAR that's being used in the wetland mapping process. The upper image, the reddish image, is a color infrared satellite image of a location in coastal Alaska. And the lower image is a LiDAR elevation model of that same area. And you can very quickly, by combining the two, search out the upland areas from the wetland areas. You can see this upland ridge that stretches through the center of the image, and just above that you can see this lake basin, which forms a topographic depression on that image. Again, it's a process of using as much information as possible to look at and define wetland boundaries and map them most efficiently on the landscape using different data types. This is just another picture of wetland mapping and the wetland mapping process in Alaska, showing kind of the density of wetland features in coastal Alaska. Again, this is that study area on the Yukon-Kuskokwim Delta in the west central portion of Alaska. The final wetland map is the one on the largest map on the right-hand side of the screen, and you can see that basically this whole landscape is wetland, and the mapping process to develop that map is intense. There's a lot of information and a lot of decision making that goes into creating that wetland inventory. So we're also developing what we're calling scalable mapping techniques in Alaska to address budget realities. In some cases, folks are interested just in a map that shows where are wetlands and where aren't wetlands, as opposed to where are wetlands, what type of wetland are they, how are they functioning, what are the attributes related to their landscape position and landform type and so on. And so we've developed several approaches to kind of higher intensity and lower intensity wetland mapping. And that's what this graphic is designed to show, is just how the level of detail increases as you move from one scale to the next. The one in the upper right-hand corner and left-hand corner is the most generalized, and the one in the lower right-hand corner is the most specific. And I'm zooming in through each one of these panels to show greater and greater levels of detail. I think that's all that I'm going to say about scalable mapping, other than to say that there are various approaches being developed to make the mapping process as cost-effective as possible. So now I'm going to move on to an example from New Mexico called the Wetland Jewels program, and talk a little bit about what the landscape issues were in this project, as well as how they were addressed through wetland mapping and the wetland inventory process. The Wetland Jewels process in New Mexico relied on identifying complexes, individual wetlands and wetland complexes that were of high value for an area of national forest, and the Carson National Forest, which is in kind of the north central portion of New Mexico. And identifying why those were important, and building consensus around a stakeholder community to take action on their preservation. So the first step in the process was to inventory the wetlands themselves and educate the local stakeholder community on why those wetlands, as we inventory them, are important. And so there was a lot of communication involved in that process, and this is some of the basic information that was shared with stakeholders as we went through the inventory process. Just defining things like Doug had already described in his presentation, some of the functions like maintaining stream flow, the preservation and creation of wildlife habitat, the provision of clean water to downstream communities, and the mitigation of climate impacts, climate warming impacts. The one thing that we find consistently from study area to study area as we take on projects like this is it's really important that stakeholders in those communities understand the value of wetlands from an ecological standpoint, but also from a value standpoint or a benefit standpoint to local communities and local individuals. So the process of identifying wetland jewels was driven by a planning process in the U.S. Forest Service, the 10-year plan revision, which happens only once every 30 years, even though it's a 10-year plan. And that planning process relies on identifying significant features on the landscape that the Forest Service will be required to or will be interested in protecting over time as part of their plan implementation. There was a planning process kicking off in both the Carson National Forest and the Santa Fe National Forest at the same time as we were updating the wetland inventory for the state of New Mexico, and that gave us the opportunity to feed directly into the plans as they were developed. This process also involved, as I mentioned before, stakeholder engagement to prioritize ecological wetland functions, and that was made possible by the fact that we incorporated some of the classification techniques that Doug had mentioned earlier, so the National Wetlands Inventory with HGM and LLWW classification tools to derive functional benefits or a correlation of functional benefits from the wetland data. Some of the functions that were identified were things like contributing to wetlands that contribute to stream flow, wetlands that contribute to groundwater recharge, wetlands that perform carbon sequestration, and so on. And each one of those was taken before a stakeholder group, and the stakeholders were educated as to what those functions and benefits were, and then were asked to rank them and come up with a ranked list of what they felt as a stakeholder community were the most important functions and benefits to be preserved by the U.S. Forest Service in their planning process. In the end, the final priority functions are listed here on this list, so contributions to stream flow, groundwater recharge, preservation of fish and aquatic invertebrate habitat, management of threatened and endangered species, surface water detention, waterfowl habitat, and so on. All of those were the highest priority functions that this particular community identified in the wetland inventory and wanted to preserve, and wanted to communicate the value of to the U.S. Forest Service so that as the 10-year plan was implemented, action could be taken to preserve those environments. So it wasn't possible to do any of this without a robust wetland inventory. And having that inventory both at a fine enough level of detail, so polygons on a map that identified different wetland types, but also classified using the variety of classification tools that were available, and then identified according to their functions and benefits, really provided the information that was necessary to justify why the Forest Service would want to spend money either protecting or restoring those wetlands on the landscape. They needed to understand the value to the local stakeholders and the local community, and they needed to justify why they would spend money on it. So this whole process ultimately ended up in the application of for funding for restoration. The mapping process led to the identification of wetland jewels, as they were called, and there are many of them across the landscape in the Carson and the Santa Fe National Forest. The U.S. Forest Service recognized the value and the stakeholder need to protect them, and they prioritized the management of them both from a preservation and a restoration standpoint, and they're now partners in several volunteer restoration projects that are occurring on the ground. And these are just a couple of pictures from one of the areas, one of the wetland jewels. Doug had mentioned earlier head cuts where erosion is occurring into slopes and migrating up slopes, and the effect of a head cut like the one you see in the left-hand side of this image is to very quickly drain out saturated slopes by providing or by creating erosive features that channelize water and drain water off these sites very quickly. Typically in New Mexico, they're caused by cattle grazing and trampling across these sites at high elevations where the soils are disturbed very quickly and water is able to focus and create higher erosive potential, and as these channels develop, these whole entire slopes drain out. There's a couple of ways that they can be addressed very quickly, and some of those examples are shown in this slide. On the upper right, the partners in this project are creating an exclosure so that the sensitive wetlands in these high montane sloped areas are protected from cattle grazing. and then some of the natural features that are used to arrest the head cuts, like this log barrier on the left-hand side and what's called a zuni bowl, or a rock barrier on the right-hand side. So again, a robust inventory process, identifying both wetland types as well as wetland functions and benefits, leading directly to on-the-ground activities to manage and mitigate the wetland challenges. So I'm now going to move on to the last example, which is one from the state of Wisconsin in the northern portion of the state along the Lake Superior shoreline. And this example is one that's been going on for quite some time, where we've got a landscape that in its natural form was highly wetland rich, as well as having significant land cover. And over time, since the beginning of settlement in that area, the land cover has been reduced due to both forestry activity and agricultural clearing, and the number of wetlands has been reduced due to wetland drainage and land recovery. And it's all happening in an environment that is really rich in clay-dominated lacustrine soils from the glacial lakes that inhabited this area back at the last glaciation. And there's some other challenges related to the topographic position of features in this area, because the clay-rich landscape that's directly adjacent to current Lake Superior grades upwards in a fairly significant topographic rise, which is dominated by sand and gravel soils. And so as water falls on this landscape, it flows down that slope and pools in the clay soils at the bottom of that slope, erodes very quickly through those clay soils and the lacustrine soils along the current coast, and incisors streams and causes lots of damage, as you can see in the photos down the left-hand side of this picture. So the challenge and the issue was to figure out how to slow the flow of that water from the upland topographic areas in the south portion of the project study area through the lacustrine landscape and into Lake Superior. The water issue, the water speed issue, and the erosion issues were all caused by the fact that water now falling on this landscape doesn't have the same amount of interception from vegetation that it did pre-settlement, nor does it have the number of wetlands on the landscape to intercept and hold it. So it's falling on this landscape, and it's very quickly running across the surface into the streams and then down the streams towards Lake Superior. It's a huge increase in drainage intensity and also drainage volume, and the natural streams in this area just are not equipped to handle it. And so they're very quickly incising and down cutting and trying to find a new level based on the new volume of water. So one of the first steps was to create an enhanced wetland inventory of the area, and we used National Wetlands Inventory and the hydrogeomorphic metrics in the form of the LLWW classification. And we also conducted a wetland functional correlation to correlate wetland types to their functions and benefits. And we created a very, very fine wetland map, fine in terms of spatial resolution, where we mapped wetland features down to a quarter of an acre in size. We also went through a process of identifying potentially restorable wetlands, because the end result of what the inventory was trying to provide in this case was an updated map of where wetlands could be managed and or restored to try and mitigate this issue of increased flow on the landscape and increased water volume and water intensity going into the local stream network. The potentially restorable wetlands were developed through a spatial analysis exercise using countywide soils data, and then some other derivative things like a CTI surface, or a compound topographic index surface, which is a measure of where water pools on the landscape, and then developing some hydraulic models, additional hydraulic models to identify different things like stream power index and other measures of how quickly water is entering streams, and then how much force it has as it flows down them. This is just a shot of the enhanced hydrologic connectivity map that we developed for this area, showing not just the traditional stream landscape, which you see in the blue lines on this image, but also the various water flow paths that are draining water off of areas adjacent to those streams, with the idea being that if some of these areas that are intensely quickly drained could be reconverted back into wetlands, which they would have been naturally, then there is more opportunity to intercept water and stop it from entering the streams as quickly as it is and causing erosion and downcutting. So basically, it was an exercise in trying to identify the areas of opportunity for land management to mitigate the issue of discharge, stream discharge. We also developed other metrics like this peak discharge map, which is a process of identifying the streams, watercourses, and watersheds that have the highest discharge over the shortest period of time, again, to provide targets for wetland management, wetland restoration, and wetland preservation. And so, in the end, turning science into practice, as a result of all the analysis we did in this particular area, we identified several actions, management actions, and you see them listed here: increased water storage through wetland restoration, improved in-channel and upland surface roughness of plantings within channels, and maintenance of vegetation along riparian corridors, as well as converting prior abandoned lands back into what they would have been traditionally, which was either forest or scrub cover. Implementing agricultural best management practices, things like crop diversity and contour tillage and livestock management. Establishing and enforcing riparian management zones along streams and rivers, and setting targets for replanting and recreation of natural vegetation in some of the highest erosive potential watersheds. So again, it's a whole process driven by wetland inventory, but also driven by science and stakeholder engagement, basically to identify opportunities for land management activity that would mitigate both wetland function, wetland location, erosive potential, and the significant negative impacts of flooding across a human-dominated landscape. And I think that's the end of what I had to say, so I will turn it back over to Jean at this point, and she can wrap things up.
Great. Thank you very much, Andy.